All right, let's get looking at section 22.4, which deals with ways to prepare amines, but these are all things that we've seen before. This is going to be a quick review. So the first one is preparing an amine from an acyl halide. No, it's from an alkyl halide, so there's a little typo there. But anyhow, how to prepare an amine from an alkyl halide. It's a two-step process. The first one is an SN2. So if you have a primary or a methylamine, you can treat that with cyanide. Cyanide is a good nucleophile. It's a weak base. And so that can just do an SN2 reaction. You have your nucleophilic attack, loss of leaving group. But what happens is you change the number of carbons in the skeleton, right? You're starting out with 1, 2, 3, 4, 5 carbons here, and then you're ending up with a total of 6 carbons in the next compound, and then you reduce that using lithium aluminum hydride, followed by treatment with water, and that is a way to make a primary amine. So that's something that we've seen already. Another option is to make an amine from a carboxylic acid, and this is something that we looked at a lot in chapter 20. We said, okay, well, if we take a carboxylic acid, we convert it to an acid chloride in the first step. So we're treating it with thionyl chloride, and we use that reagent many times in chapter 20. So just to give you an idea, after you treat it with thionyl chloride, you make the acid chloride. Then you treat it with excess ammonia. And of course, you need excess to mop up the HCl, so to speak, because HCl is so reactive. And so then you end up with a primary amide, but then you can reduce that oxygen off and replace that with 2 hydrogens. And to do that, we use lithium aluminum hydride in the first step, followed by treatment with water. So that's another way to make a primary amine. So, and of course, you could make a secondary or a tertiary amine if you were to use something other than ammonia, if you used a primary or secondary amine. Another way to make an amine was to make aniline, right? We talked about this in chapter 18 when we discussed electrophilic aromatic substitution. First, you do a nitration reaction using nitric acid and sulfuric acid. That makes the nitronium ion that we talked about in detail. So you make the nitronium ion, which is a really powerful electrophile. So that looks like this. And then this can come in and act as a nucleophile like that. And we talked all about that. You make the sigma complex, you do the proton transfer to restore aromaticity, and you can make nitrobenzene. Now, in chapter 8, we talked about, chapter 18, we talked about reduction using hydrogenation to reduce the nitro. So this is hydrogenation, which works very well to reduce it to make aniline. Okay, but another option we said was to treat it with iron or zinc and acid. Right now, we didn't talk about tin. I don't remember anyhow. Tin, or this is tin 2 chloride. And there's an advantage to using tin, and I'll get into that in a second. But you could use any one of these, iron, zinc, tin, or you can use tin 2 chloride and acid, followed by treatment with sodium hydroxide. So I'll put new by this one here, so new. And the reason why you need to have the sodium hydroxide in the second step is because, remember, you end up making the aniline ion, right? You end up with NH3 plus, and then to remove that extra proton, that's why you have to treat it with the base, okay, in the next step. All right, there we go. So, yeah, so with all this in mind, why don't we try a problem where we kind of are forced to revisit some old chemistry. It says draw the structure of an alkyl halide. So we want to start with an alkyl halide or a carboxylic acid that might serve as a precursor in the preparation of each of the following amines. Okay, so let's say you wanted to make the first one. So this would be 1-butane amine. And if we wanted to make this using an alkyl halide, well, we would use cyanide as our nucleophile. So for that, we'd start with something like propylidide. So propylidide, in the first step, we treat it with sodium cyanide. In the next step, we would treat it with LAH. Getting ahead of myself here, to reduce it. And then, of course, you have to treat that with water in the last step. So I can make a better 3. There you go. And you're going to treat that with water in the last step. and that would give you 1-2-3-4-1-butanamine, right, which is the desired compound. Now, if I wanted to start with a carboxylic acid, I'd have to start with 4 carbons to begin with. So I'd start with a carboxylic acid with 4 carbons, 1, 2, 3, 4. So this is butanoic acid. What would I do first? First, I'm going to treat it with thionyl chloride to make the primary amide. Then I'm going to treat it with excess ammonia. That's going to make the primary amide. We've seen this today. Then I'm going to treat it with lithium aluminum hydride, followed by treatment with water. And that would also give me the desired primary amine. All right. I'm going to switch over to a blank document for B. So let's go over here. So go over here. I think there's some space here. And in B, so this is 22.10, and this is B. So we want to end up with this compound. And remember, we're asked to come up with a couple of ideas. The first one with an alkyl halide. Well, if I want to use an alkyl halide, I use cyanide as my nucleophile. So the carbons that are on the left-hand side of this blue squiggle, that's going to be the carbons in my alkyl halide. So I would want something like this. So this is going to be benzyl bromide. If you put iodide or chloride, that's fine. In the first step, you're going to treat it with sodium cyanide. This time I'm going to draw more of the intermediates. So you end up with the CH2. Then you've got the nitrile like this. Then you're going to treat it with lithium aluminum hydride, followed by treatment with water. And that is going to give you the desired product. So now you've got the extra carbon on there. There you go. So that would be 2-phenylethanamine, I guess is what you would call that compound. The next one is you want to do it from the carboxylic acid. So in terms of retrosynthesis, right, you want to have this amide is the way you would write this. So you'd have the carbonyl here. Okay, so now we just need to make the desired carboxylic acid. So what are we going to do? Or it says you can start with the carboxylic acid rather. So we would start out with the right number of carbons. So that means we'd start it with this compound. First, we treat it with thionyl chloride, SOCl2, followed by excess ammonia. That gives us that primary amide that we wanted. And then we know that we can reduce the carbonyl to a methylene by first treating it with lithium aluminum hydride, followed by water. And that's going to give us our primary amine. So again, we get 2 ways of making the same thing. I'm going to skip C because it's very much in the same vein as these ones. And so we're going to move on from there, and we're going to look at some new ways to make amines. And we'll start with section 22.5 now. So preparation of amines via substitution. We know that amines can undergo substitution reactions because we saw already today that amines make good nucleophiles, right? They have that lone pair with that electron density that is ready to attack an electrophile. And so amines, again, are good nucleophiles and readily undergo SN2 reactions with an alkyl halide, right? Especially if it's a primary or a methyl halide, right? Then we're going to get SN2. So you can see you've got your nucleophilic attack here, loss of leaving group. So that, again, is just an SN2 reaction. And then you end up with an alkyl ammonium ion. So this would be methyl ammonium iodide. And then you still have ammonia kicking around. And so that can do a proton transfer. And then you end up with the primary amine. So it says that this is an efficient way to make a quaternary ammonium salt, because you notice that this last step is in equilibrium, and this is the quaternary ammonium salt, or we sometimes call these quats. So quaternary ammonium salt. But the thing is if you have an amine like ammonia, and we just saw how to make this compound, didn't we? Okay, and how it can get deprotonated in equilibrium to make the primary amine. But check this out. Once you've made the primary amine, if you have other or excess iodomethane in your reaction mixture, it's going to react again. In fact, this methyl group is actually going to donate some electron density via hyperconjugation. And now this is even going to be a more powerful nucleophile. So the second reaction occurs even faster. You end up with the dimethylamine, okay? And then that's going to act as a nucleophile again, an even better nucleophile. Then you end up with trimethylamine. And as you saw, that can act as a nucleophile too to end up with your quaternary ammonium salt, your quat. So this is kind of like a runaway reaction of sorts, okay? So it says right here, again, and I'm repeating it, it says monoalkylation, like to make this compound is pretty damn difficult because it just keeps reacting and reacting and reacting, and it's very difficult to stop it. I mean, I think I've tried this reaction before where you just add one equivalent or something, and you always end up with a mixture. So we call this exhaustive alkylation. Because you just keep adding alkyl group after alkyl group in exhaustive alkylation. Well, there's another synthesis that we can use, which uses another substitution besides using cyanide, and that's to use azide. So azide is N3 minus. Okay, so this is an azide ion, and you can take a look at the Lewis structure of an azide, which looks something like this, where you have a negative charge here and here, and then you have a positive charge like that. So the azide can also act as a nucleophile. It says here, azide synthesis, conversion of an alkyl halide to an azide via an SN2 by reduction to yield a primary amine. And so if we have a primary alkyl halide and you want to convert it into a primary amine, but you don't want to add a carbon to the skeleton like you did with cyanide, well, what do? You use azide. So look, azide has an overall negative charge. It's going to do the nucleophilic attack, loss of leaving group, to make your alkyl azide, and then you can reduce that either by hydrogenation or by using lithium aluminum hydride followed by water. Remember, if you're wondering, didn't we see something similar to this already today, Mr. Dion? Yes and no. Because, yeah, you can do an SN2 with cyanide. However, look, you've got 1, 2, 3, 4, 5, 6, 7. You end up adding a carbon to the skeleton. So adding, or let's put here, adds 1 carbon. And then here does not add a carbon. All right, and so this is a better way to make a primary amine than trying to alkylate ammonia. Much better way of doing it. Now, the only caveat, I think, to making azides, and I've never made an azide before in my life that I can remember, is that these are shock sensitive. I think that azides are pretty explosive. So we'll put here explosive. So there must be some precautions that you have to take if you want to make an azide, and some end runs that you can do around making an azide as well. If you go to the next slide, it's just a mechanism showing you some of the details of what I showed you before. I showed you the nucleophilic attack of the azide ion, but this actually shows you the reduction or the elimination of nitrogen to make the primary amine. So you have a nucleophilic attack by a hydride, you lose nitrogen, then you have another proton transfer in the end, okay, to make your primary amine. And I think this is a good mechanism to familiarize yourself with. Now, instead of, making azides, which can be explosive, there's another way to make primary and secondary amines called the Gabriel synthesis. And I think that this will avoid having to make those explosive azide intermediates. And you start with this molecule called phthalimide, okay? And phthalimide is not phthalimide, but phthalimide is a commercially available compound, okay? And the first thing you do is you convert it into potassium phthalimide. Very simple reaction. You just take it, you treat it with a strong base. The base is a proton acceptor. The mechanism is exactly what you're thinking. You just rip this proton off, right? And you end up with 2 lone pairs, 2 bonds on your nitrogen. It's got a negative charge. So you end up with potassium phthalimide. But the thing is that potassium phthalimide now makes a pretty good base. Okay. Now the pKa of phthalimide, it has a pKa of around 8.3, I think, or something like that. And the pKa of water is 15.7. So of course you can see that the equilibrium is going to lie to this side right here. Now, once you've got potassium phthalimide, it can then be alkylated. How does it do that? It does it in an SN2 reaction because this is going to be a good nucleophile. The phthalimide ion is a good nucleophile. You have your nucleophilic attack and your loss of leaving group. Then you basically end up just tacking the alkyl group onto the phthalimide is all you're doing. Now, there's got to be some way to excise this from all of this over here. And the answer is yeah, there's actually a couple of ways to remove all that piece. One way is to just treat it with aqueous acid, and then you end up hydrolyzing both of the amides. Now that's a sluggish reaction because you know that amide hydrolysis in acid is not the greatest reaction in the world. You end up with this molecule here. This is called phthalic acid, okay? And then you end up with an ammonium ion, right? You end up with an ammonium ion. So you have to take this, then you got to treat it with sodium hydroxide in order to make the amine. But if you just want to make the amine right away, you would react it with hydrazine. So remember, this is called hydrazine, okay? And that's going to give you this strange intermediate here, or I should say interesting intermediate. And then you end up with the uncharged amine. So I'll be honest with you, I've graded a lot of quizzes over the years, and my students always prefer to use this method here. Why? Because you end up with something that's uncharged, okay? And they're like, I want to avoid any extra steps like this, okay? And there's no problem with that if you're doing the chemistry on paper. However, you do need to be familiar with both ways. So I'm going to give you a second while I take a drink of water to give this one a try, 22.12, and you want to use the Gabriel synthesis. I'll help you out. The first step is that you want to start with phthalimide. We're going to do the whole thing. We want to start with phthalimide. So we've got this 5-membered ring here, and you've got a nitrogen with a hydrogen on it. So the first step is you're going to treat it with potassium hydroxide. Okay? And I'm going to give you a second to think about the next 2 steps. And I'm going to take a drink of water. We'll give it the old college try. All right. So let's see what we got here. First step was to treat it with potassium hydroxide. Remember that all of this portion that I'm going to put in the blue box, this is going to come from your electrophile. So that means your electrophile has to contain the cyclopentyl group, the methylene, and then you've got to have your leaving group here. So let's choose bromide just for fun. You could choose chloride or iodide. That works too. And then in the last step, if we want to end up with an uncharged amine, we're going to treat this with hydrazine. So NH2, NH2. And that's going to give us the final product, just like that. Okay, same kind of thing here. Again, everything that's not part of the amine, all of this here is going to have to come from your alkyl halide. So we're going to start out with phthalimide. Draw our phthalimide molecule. That first step, we're going to treat it with potassium hydroxide. Everything that's inside that red box is going to have to be a part of our electrophile. So we'll write, got the 2 aromatic rings, the carbon in the middle, and then we've got our alkyl halide. I'll put iodide here. You could put bromide or chloride. And then in the last step, you want to treat this with hydrazine. You end up with an uncharged molecule. There we go. All right, another way to make an amine, whether it be a primary amine, secondary amine, or tertiary amine, is to do a reaction called reductive amination.